Well, my talk will follow nicely from the previous one in that I'm looking at selecting species of trees. My trees are pretty much fixed in place, as is my presentation, so forgive the lack of animation. Um,
Really fixed
and pressing the arrow doesn't seem to do anything. There we go. Okay. Vegetation, as we know, is just one strategy for improving outdoor thermal comfort. Um, um, Provides shade and does other things to talk about in a minute. Urban geometry, another shading from buildings, shaded pathways, and so on, and then materials and their surfaces. They have different benefits, and they're characterized, conditioned by both the site, the climate, neighboring development. So to look at trees, the energy balances is shown in the figure on the right, and we're familiar with most of that. The transpiration, interception of shortwave radiation, and so on. Trees can reduce this shortwave radiation, surface temperature, and heat accumulated in the soil, reduce MRT, mean radiant temperature, and therefore improve thermal comfort, modify air temperature, but they also increase air humidity and can reduce wind speed. Which impacts thermal comfort and maybe transport of pollutants. So in Singapore and elsewhere, the question is, do trees provide acceptable thermal comfort conditions? And this study was prompted by efforts to provide information about tree species selection for the relevant authorities. Singapore, tropical, not much annual variation in temperature. The data has shown lots of rain, 2.4 meters over the year, and monsoon season. So in the temperatures are highest in between the monsoons, and humidity is relative humidity is very high, particularly at night. This study is largely experimental. It took place in a park, a linear park, which serves as a floodplain for rivers. So the water, which used to be in kind of a concrete trough, is now open, and in heavy rains it can just spill over. We had two measurement campaigns. The one I'm going to focus on is the second one a week, where we took measurements under and beside the 6 trees shown in the map. We had two kinds of measurements. One was to characterize geometry and leaf structure, and we did that with a LiDAR like a P40. Took 4 scans per tree, formed the point cloud by merging the images, obtained geometry as shown, height, crown height, trunk height before the crown, and then the diameter of the crown and the trunk. And with that, we could determine leaf area density and then plant area density, which included the woody matter, and integrate it vertically to get the leaf area index and the plant area index. So we did that for the 6 trees. For the climate measurements, we had 2 tripod-based instrument ensembles. Both used Vaisala, which has the 2D wind speed and direction, temperature, humidity, and rainfall. We had globe thermometer to get input for MRT. And we used, for the one beside the tree, we put another temperature sensor in an aspirated shield to make sure we were rejecting the impact of shortwave radiation. And so those measurements were done under the tree, was half a crown radius away, and outside was 2.5. Oh, and then we had the global horizontal and the diffuse horizontal radiation. We had 6 species which were used in this park, and you can see the data that came from the measurements. These were done in daytime hours, and we did 2 trees per day. Each tree was evaluated 2 to 3 times. The weather conditions varied over the week, and therefore the measurements for any given tree varied as well. No day was completely clear, so here's one of them. where this is the global horizontal, and here's the diffuse. So the diffuse is higher than you would get on a clear day, and then under the tree, they're essentially the same. When temperatures are high, humidity is low, and then the wind speeds were almost always low, about a meter a second. Okay, some results. So each row here is for a tree in 30-minute segments. And so for T1, there were two passes over the course of the week. Blue shows reduction in air temperature, which is typically small, under the tree compared to beside the tree. And then the lower is vapor pressure, where this should be hundreds of Pascal, hectopascal, and there's some increase in vapor pressure under the tree. Reductions in air temperature relative to beside the tree are typically small, averaging less than 0.3. In morning and evening, they can even be a little higher due to radiation trapping, long-wave radiation trapping. The MRT that we calculated is inversely proportional to the radiation. Where radiation is high, under the tree you get the biggest difference from shade in reduction of MRT. And the converse is true. If the radiation is low, then your reduction of MRT is smaller, as expected. MRT, we have the same way of displaying the data, where the darker blue colors show more reduction in MRT under the tree. That highest reduction is associated with trees with the lowest transmissivity of solar radiation, which is a fraction of what's under the tree compared to beside it. Tree structure matters, so we have two trees here with the same view of the sky view factor, but different transmissivities due to leaf structure, and they will have T12 compared to T1, bluer colors, so more reduction in MRT. We have calculated PET, physiological equivalent temperature, for our thermal comfort index, and did a multivariate linear regression. Most of the variation, the depression in MRT, most of the variation in PET and how that varies under the tree compared to beside, that difference can be associated with the difference in shortwave radiation and its impact on MRT. Air temperature also has an impact on it. Okay. And then looking at thermal comfort over the day, where the acceptable region, based on work that our colleagues have done, is from caps at about 31.6. Ambient temperature, or PET, beside the tree, this light blue, is almost always above the acceptable limit. So if you're in the sun, Peter and others have been there, know full well that's the case. We then categorize that over the day, beside the tree and outside the under the canopy, by a metric, outdoor thermal comfort autonomy, which gives you the fraction of the time that the conditions are acceptable, and then a deviation which is in average degrees above, in this case, the maximum limit. So some of the trees did pretty well. Under the tree, 44% of the time it was comfortable on the days the measurements were taken. The fig tree, the ficus, was 0 in all cases. Never comfortable outside it. And then to get away just from the weather patterns that we were using, did trees around different days, we modeled PET as a function of the variables. We had primarily air temperature and then the global horizontal radiation, both beside the tree. So for each of them, we could make a map of GHI and air temperature, and then the PET is shown from low to high in the false colors. So T9 is the ficus, so it's mainly the hotter colors. It's hot, and ones that do better, you get the bluer colors. So that's a way of comparing trees over the kind of the same conditions. extended work. One more. Oh no, this is it. Okay. So most of this is, I think, kind of apparent from the data. They do have different thermal performances. Even though they may be uncomfortable under the trees, some are all of the time, they all have a reduction in thermal stress. What we hope to do going forward, the first one is particularly interesting to me. We're going to extend the model to account for the tree geometry and the leaf structure. And then, do I have a minute left? Yeah, great. And then also do this kind of modeling under weather types. We have about 7 that cover the course of the year. So then we can compare trees over a year on sort of an apples an apples basis, and then extend that to clusters of trees and forested areas. And whether this goes or not, I'll thank you for your attention. This was problematic, and happy to answer a couple questions.
Thank you. It was very on time. Some questions? Yes, please.
Thanks very much for the talk. Fantastic to see so much, thoroughly collected data under the canopies. I was wondering, you showed the wind speeds were generally extremely low, around the sort of meter a second. I mean, I don't know very much about the fine meteorology of Singapore, but is that a sort of a typical kind of wind speed? For
It is. Even when there are heavy rains, they're not really strong winds, so it is typical.
Okay. Thank you.
Yeah, now the regressions would account for that. I mean, if it were windier, we could pick that up in the data, but that is typical.
Yes.
Okay, thank you. I suppose this is some data from measurement. So a question not that relevant, but do you think for tree simulation or models, do you think the model should be turned in terms of the climate context? Because different trees, their function maybe some are for shading in some climate and some maybe for evaporation, but some function may be suppressed in the different climate context. Do you think it should be certain type of like a treatment of the model?
Certainly, and that's a good observation. So it's very humid there. You don't get as much evapotranspiration and so on. So this sort of thing, if it could be considered a method, would be climate specific.
Okay, thank you very much.
Thank you.
Yeah. Okay.